In this video, we are going to walk through number 9 from the Unit 8 review packet. It asks us to find the volume of the solid created when the region between F and G is revolved around each line. Then use the integration capabilities of a graphing calculator to verify the results. The functions are f of x equals x and g of x equals 0. And we're looking at the interval from 0 to 4. This mixes it up a bit. Part A asks to revolve around the x-axis. Realizing that the x-axis is horizontal, that is a direct implication for us that we're going to use either disk or washer depending on whether or not there's a gap. Part B is asking us to revolve around the y-axis, which immediately, because the y-axis is vertical, tells us we have to use the shell method. If I scroll to C, ask us to revolve around x equals 4, which is another vertical line. Therefore, we're going to use the shell method. And D asks us to revolve around y equals 4, which again is going to be either disk or washer because y equals 4 is horizontal. So I just want to really iterate that point that if you are revolving around something horizontal, you are going to use either the disk or the washer method. It'll be a disk if there's no gap in the region where you're revolving around. It'll be a washer if there is a gap. And if you revolve around something that is vertical, such as the y-axis or a vertical line, you'll use the shell method. For all of these, we need to see the region that we're revolving. So I'm going to jump to the solutions, and here is a sketch of the graph. So you can see that f of x equals x, I called y1, and that's for the calculator purposes. I put it in as my y1 function. That is the line that goes through the origin with a slope of 1. And y2 I called g of x equals 0, which of course is just the x-axis. So the region we're looking at here from 0 to 4 is this triangular region from x equals 0 to x equals 4. And if we were simply looking at it with respect to the x-axis, the function for f is our upper function, and the y-axis would be our lower function. That could change depending on what we're revolving around. So let's take a look at part A. Part A asks us to revolve this around the x-axis. Well, if we're going to take this region and revolve it around the x-axis, the region is right up against the x-axis, which means this is a disk. The disk formula is based on the geometric formula pi r squared. So all we need to decide is what is our radius. I drew in this cross section here, which I will redraw in red. And that cross section is our radius. So because it's the f function back to the x-axis, we can just call our radius f of x, which is just x. So the integral is pi times the integral from 0 to 4 of our radius x squared dx. Now, the expectation is that you can finish this problem. You'll notice this does not say just set up, so we have to do the entire problem this time. So I'm going to scroll down. Pretty simple problem to finish out. Pi stays out front. The integral of x squared is x to the third times 1/3, or x to the third over 3. We'll evaluate from 4. Well, we'll start with the upper limit of 4 minus the lower limit of 0. Works out nice with that lower limit of 0, so we end up getting 4 cubed is 64 over 3 times the pi is 64 pi over 3. In the calculator, you could easily do this as well. Pi times the finite integral of y1 squared, and it is key that you square the y1, comma, with respect to x, comma, from 0, comma, to 4. You would get the approximation 67.021, which is equal to 64 pi over 3. Part B asks us to revolve this region around the y-axis. Instantly, we should be thinking shell method because the y-axis is vertical. The shell method is based on the geometric formula 2 pi times the radius times the height times the width. So 2 pi will go in front of our integral. We'll still integrate from 0 to 4 because those are the x values of our region. Our radius is the difficult part, if you will, but in this case it's pretty easy because if I draw in a radius from the region I'm revolving around back to my cross section, that is simply the value that we move on the x-axis, so from 0 to wherever it is. So our radius is just x. Our height is simply the height of this cross section, which is what we just used in the prior problem, part A, as our radius. So the height for shell and the radius for disc and washer end up being the same thing. So our radius for this shell problem for part B is x. Our height is the function f of x, which is just x as well. And then our width is dx. So our integral will be 2 pi times our from 0 to 2 pi times the integral from 0 to 4 of our radius times our height dx. Interestingly enough, it's very similar to the one that we just did. 2 pi times the integral from 0 to 4 of our radius x times our height x dx. So the integral that we're doing is the same, it's just we have a 2 pi out front. So the integral of x squared is x to the third times 1/3, or x cubed over 3. Upper limit minus lower limit. We end up with 64/3 again, but this time it's times 2 pi, which is where we get the 128 pi over 3. In your calculator, you could set it up very easily. 2 pi times a finite integral of x times y1, comma, with respect to x, comma, from 0, comma, to 4, end it, enter, 134.041 approximately, which is equal to 128 pi over 3. Part C asks us to revolve around x equals 4. X equals 4 is a vertical line, so again we've got volume by shell. I'm going to scroll up real quick to the function. So x equals 4 is right up against our region. So I'm just going to erase real quick and reiterate this. The shell method is based on the geometric formula 2 pi times the radius times the height times the width. So 2 pi goes out front. Our integral is still 0 to 4 because that's still our region. Our radius, however, if I draw in a cross section and then I draw in a radius from my region back to the cross section, this is not just x. Remember, x goes from the y-axis to wherever your cross section is. So what is this distance? Well, keep in mind that from the y-axis to what we're revolving around is a distance of 4. So if this whole distance is 4 and this distance is x, then that means our radius is 4 minus x. So to set up our integral, it'll be 2 pi times the integral from 0 to 4 of our radius, 4 minus x, times our height, which is just the f of x function, x, dx. So if I scroll back down here to the work, here's the integral, 2 pi times the integral from 0 to 4 of our radius, 4 minus x, times our height, x, dx. In this case, in order to integrate it, we have to distribute the x. So we get 4x minus x squared. This is pretty easy to integrate. So the integral of 4x, x will go up to the second power times 1/2. So 1/2 times 4 gives us 2x squared. The integral of negative x squared goes up to x to the third. The negative out front times the reciprocal of 3 is 1/3, so minus x cubed over 3. Upper limit minus lower limit. Nice that we've got some zeros in here. A little bit of fraction work to get to the 32/3 times 2 pi, and that gives us 64 pi over 3. In your calculator, again, real easy, 2 pi times the finite integral of our function 4 minus x times y1, which you could type in as 4 minus x times x, comma, with respect to x, comma, times the lower, or from the lower limit of 0, comma, to the upper limit of 4. Close it up. approximately 67.021, which equals 64 pi over 3. Just so you know, it is just coincidence that part C and part A have the same answer. Part D asks us to revolve around y equals 4. If we go up top here and take a look, y equals 4 is a horizontal line, so we automatically know we're looking at either a disk or a washer. And in this case, we're looking at a washer. Why? If we revolve this region up over y equals 4, there's this gap here. So if we have a gap, we know that it's a washer. If we're going to do the washer, similar to the disk, it's based on the geometric formula pi r squared times the height. So we have to decide what our radius is. And in the case of a washer, you have an outer radius and an inner radius. Your outer radius is always going to be whichever part of your region is farthest away from what you're revolving around. So we're revolving part D around y equals 4. What part of this region is furthest away? Happens to be the x-axis. And the x-axis, no matter, oh, that's a terrible line, but no matter how you draw your line, this distance is always 4. So our outer radius is simply 4. Our inner radius is from y equals 4 to the inner part of our region. Now, some people would be tempted to just call that f of x. However, f of x goes from our linear portion of the function down to the x-axis. So if this is f, and the whole distance down is 4, then our inner radius here is actually 4 minus f. So to set up our integral, it'll be pi times the integral from 0 to 4, because that's still our region, of the outer radius, which is 4 squared, minus our inner radius, which is 4 minus the function f, squared dx. So as I scroll down here, here's the setup. Pi times the integral from 0 to 4 of our outer radius 4 squared minus our inner radius 4 minus x squared dx. If you simplify in here, you end up getting 16 minus this whole thing FOILed out. Now I didn't show the work for that, but you would have to FOIL this and then distribute the negative sign. So if you FOILed this out, it would become x squared minus 8x plus 16. Interestingly enough, the 16 here minus the 16 there cancel out, so you just end up with negative x squared plus 8x. Easy to integrate. Negative x squared goes up to the third power times 1/3, so it's negative x cubed over 3. The integral of 8x, x goes up to the second power times 1/2, which is where we get the 4x squared from. Upper limit minus lower limit. Got some zeros in there, which is always nice. A little bit of fraction work to get to 128 over 3 times pi, and there's your answer, 128 pi over 3. Could do it on the calculator as well. Pi times the finite integral of our outer radius squared minus our inner radius squared, comma, with respect to x, comma, from 0, comma, to 4, and we get approximately 134.041, which is equal to 128 pi over 3. One reminder, as this may be one of the last videos you watch before you take the AP test, you'll notice that any approximating that I did in anything involving the calculator, we always approximate to 3 decimal places.